So in our first introduction to statics, we had a look at all the forces acting on a particle. In this one, we're going to have a look specifically at strings. So what happens if a particle is either attached to two strings or threaded onto them? So these are the two key cases which we're going to look at. Either you want to look out for this word threaded, because that means that this whole piece of string here is all one string, and as we know that it's light and inextensible, we know that the tension is the same throughout. So when we put our tension onto the diagram, we can quite happily put T and T on both parts of the string because it's all one. However, if it says attached to the end of two inextensible strings, these two strings, one here and one here, are not the same string and therefore their tensions might be different. So in this case, we're going to have to call that T1 and T2. Just as a side note, do make sure that you're using capital T for tension as lowercase t is for time. So here we are with our first question. We're told a smooth bead Y, so we know that straight away there's no friction on that particular bead. It's threaded onto the light inextensible string, so we know that it's all one string. So here we can put our tension, and here also tension, they're going to be the same value. And that string is attached to two fixed points at X and Z. The bead is held in equilibrium, okay, so we know that it's static, by a horizontal force of magnitude 8, so it's just telling us about this force here, and that's acting parallel to ZX, so that's acting in our horizontal direction. The bead Y is directly below X, that's helpful to know so that we know that's acting vertically for that bit of tension, and we're also told this angle here. As soon as we've got an angle, we know that we're going to have to do a little bit of resolving. So I'd be tempted at this stage to just draw my dotted lines on to make that a right angled triangle. After that, we're also going to have to consider the fact that the bead will have a mass, so it's going to have a weight going down, which we'll call W. Okay, so in our normal fashion now, we're going to start highlighting our horizontal and our vertical forces. So let's start off by doing the horizontal. We're going to have this component of the tension acting at an angle, and we've also got this 8 Newton force acting there. We would also have in the vertical direction this component of the diagonal tension, this component of tension, and the weight of the particle there. So we're going to have a green and a yellow equation as our starting points. Then we'll be able to use them to find the unknowns. So we're going to resolve vertically here, and I'm going to choose upwards. So I've got T plus T, and as that angle is 30, this one is 30 as well, so I'm looking at the opposite here. So T sine 30 minus W, and that's got to be equal to 0 because it's stationary. And I'll also resolve to the right, so I have T cos 30 minus 8 equals 0. And I'll call that equation 1 and equation 2. Looks like equation 2 is going to be very helpful to find the tension in the string. So if we rearrange that, we're going to have T equals add the 8 and then divide by cos 30, giving us a tension of 9.24 newtons, correct to 3 significant figures. Then we look at part B, which is finding the weight of the bead. So we'll rearrange equation 1 for this. Just go back and note that that was equation 2 that we used there. Equation 1, so W is equal to 9.24 plus 9.24 sine 30. As usual, to try and be as accurate as possible, use the answer button on your calculator rather than the 9.24. And that will give us 8 root 3, which comes out to be 13.9 newtons, correct to 3 significant figures. Next situation, we've got a small bag of mass 10 kilograms. Okay, so as soon as we've got that mass, we know that we can put our weight on the diagram. Weight is mass times gravity, so it's going to be 10g. It's attached at C to the ends of two light inextensible strings. That's telling us that these two tensions are different, so I'll call that T2 and this T1. The bag hangs in equilibrium, so we know it's static, and we're given these angles 30 and 60 degrees relative to the horizontal. So, better draw ourselves the right angle triangles. Much better to choose the two right angle triangles that I've drawn rather than going for a vertical line up here, because then you'd have a shared line between T1 and T2 and it could get confusing. Okay, start highlighting then. So vertically we've got this bit of T2, this bit of T1 and 10G. Horizontally we've got this bit of T2, this bit of T1. So we'll have a green and a yellow. Very similar to the last case, so pause the video now and see if you can get the green and yellow equations and then come back and check. Okay, so we've got our two equations now, but looking at them straight away, we know that there's no easy way to solve these, so we're going to have to do some simultaneous equation solving. I'd be tempted to take equation 1, rearrange it and make T1 the subject, and then substitute that into my second equation. So if I make T1 the subject, it's going to be T2 cos 60 over cos 30. Practice doing that rearrangement yourself so that you're happy with it. Then I'm going to put that into equation 2. So I'm going to have T2 cos 60 sine 30 over cos 30 times. So quite a long first term. Then we've got plus T2 sine 60 minus 10G is equal to 0. We're going to need to bring T2 out as a factor, and then we can divide by that whole bracket. So if I bring T2 out here, we're going to have cos 60 sine 30 over cos 30 plus sine 60, and we can move that 10G over to the other side. So to get T2 now, all we're going to do is 10G from this side divided by that entire bracket there. So you are going to want to probably use the fraction button on your calculator. That will help out with getting everything in the right place. After all of that, that will come out to be T2 equals 84.5 newtons. So T2 is, when we look back at the question, we're going to just work out if it's AC or BC, and that AC is T1, so we've just worked out BC. So this is the answer for part B. Now I'll just quickly pop back and do part A, and I'll just make myself a small side box here so you can see it all in one go. And I can just sub that right back in to my rearranged equation 1, which I did over here. So that's going to give me my T1 value now using the T2 that I've just worked out. As it happens, it comes out to be a lovely value of 49 newtons. So there's the answer for part A. Now we're going to start moving back towards familiar territory, where we're expecting to have two particles connected by a pulley on an inclined plane. So we're told that we've got a mass of 3 kilograms sitting on the smooth plane, so we know there's no friction. So therefore, it's just this 3 kilograms going to cause a weight of 3G there. We'll always have a normal, and we're definitely going to have tension in this string, and as it's a pulley, same thing applies as before, tension's the same throughout the string. We're then told that the cable carries a mass of 1 kilogram freely suspended at the other end. So down here we've got a force of 1G or just G. We can quickly just draw some right angled triangles in, which will help us with our resolving. And we've got to calculate the magnitude of P and the normal reaction between the mass and the plane. So do a little bit of highlighting to start. Pause the video, make sure that you're able to do this section by yourself. Okay, so now that everything's highlighted on the diagram, I'll start off with my blue equation and I'll resolve downwards for that, giving me G minus T is equal to 0, so straight away that tells us that the tension in the string is 9.8 newtons. Yellow equation now will resolve up the slope, so we'll have T plus P cos 45, because P is also forcing it upwards, minus 3G sine 45 is equal to 0. And then if we resolve in the direction of the normal, we're going to have the normal minus p sine 45 minus 3g cos 45. So we've used up equation 1 already for t. So equation 2 and equation 3 is what we use next. For us to find the magnitude of p, equation 2 is going to be useful for that. So rearranging, we're going to get p cos 45 equals 3g sine 45 minus t, and we know t to be 9.8. So now we've got p being equal to 15.5 newtons. Secondly, we can find the normal reaction between the mass and the plane, and we're going to need equation 3 for that. And that's just going to be a straight rearranging for us. So normal is 3g cos 45 plus p sine 45, and we know the value of p now, so we're just substituting that in. And that gives us our normal value of 31.7 newtons, again rounded to 3 significant figures. As a final point at the end, do make sure that obviously you're practicing these same techniques in statistics now that we did in dynamics before, but when you get closer to your revision time, do just make yourself a mental note that it doesn't always equal 0. It's only when it's static, otherwise it would equal ma if there was any acceleration.